Hello everyone and welcome to this webinar about hardware-in-the-loop testing of electric motor controls. My name is Carlos Villegas and I am the Electrification Industry Manager at Speedgoat. I'll be presenting together with Shankar Abhinav, a Senior Application Engineer at MathWorks. I'm also covering for Manuel Fedu, who could not join us today. Manuel is a Senior Application Engineer at Speedgoat. So why should we consider hardware-in-the-loop testing for electric motor control developments? Let us use an example to show the advantages of using hardware-in-the-loop or HIL testing for short. Let's say your team is responsible for testing the motor drive controller of an electric car powertrain. And the first traction inverter controller board have just been made available for testing. For many teams, the next logical step is connecting these control units to the physical plant, like it could be a power inverter and electric motor. But this approach may neither be the safest nor the quickest path to finalize your project. That is, as when energized electrical drives could be an electrical hazard, and you may not want to test them with early stage controllers. So it makes sense to minimize the risk of damaging equipment by first connecting your controller to a virtual plant using HIL testing. Getting time with a dyno setup or power lab might also not be an easy thing to do. As you can carry out HIL testing in the meantime, you're benefiting in terms of time and cost. Finally, it's rare that everything lines up the way it was planned in the initial setup. And HIL testing lets you be less dependent on hardware lead times and lets you test faster. For all these reasons, many engineering teams apply HIL testing to thoroughly validate embedded controllers before testing with the real system. But what exactly do you need to implement a HIL system? There are typically three main components. First, your system under test. This may be a production controller that requires thorough testing. The system under test may also include other real components like domain controllers, sensors, and actuators. The system under test may also be an electrical equipment with not only control but also power interfaces, like it could be with an electric motor drive. The second component would be a HIL test bench with a real-time simulation of your virtual plant. It could also be composed of I/O modules to interface with the system under test, like it could be different control signals, data acquisition, signal conditioning, and communication protocols. It could also include different means for plant emulation, like power amplifiers in the case of motor emulation. And third, a workstation running application software that supports the setup, operation, and data logging of the HIL test bench. Let us have a quick preview of our HIL testing demo of an electric motor controller. We have an embedded microcontroller running Simulink-based motor control algorithms with digital and analog I/O interfaces. This is our system under test and includes a host model to adjust speed and other set points. And we deploy the motor and inverter plant model to the Speedgoat real-time target machine. The Speedgoat real-time target machine acts as a HIL simulator that runs the motor and inverter models in real time. It interfaces the control signals with the virtual motor and inverter. The Speedgoat real-time system is our HIL test bench and our desktop PC will be our workstation. Our plant consists of a permanent magnet synchronous motor subject to a constant torque. Therefore, at the beginning, it will start spinning. On one click, we can start the HIL simulator with a motor and inverter running on a Speedgoat FPGA. And now we switch to a screen with the host model of the embedded microcontroller we have on the left. On the right, we have the measured phase current and quadrature encoder counter. As we start the motor controller, the motor starts spinning in the other direction and tracks the speed. As we change the reference speed of the controller, the virtual electrical motor adjusts and also changes speed as we change the set point. Now, which technologies are required for HIL testing of motor controls? First, you need to simulate the electric drive. So you need models for electric motors, power converters, and also for the electrical and mechanical environment. And you'll need to run all of this in real time. Then you need to connect to your system under test. If it is a controller, you'll typically be interfacing with control signals and with communication protocols. But if you're working with an electrical equipment, then you're also going to need to have power interfaces. You may also want to automate testing, so you need technologies for automation and instrumentation, as well as report generation. We will cover how Speedgoat and Mapcore solutions support all of these enablers. The outline of the remaining part of this webinar looks as follows. First, Abby will discuss modeling techniques and desktop simulation of electric motors and their inverters. Then we will present a demo of hill testing of an embedded motor control, followed by a power hill testing of an electric motor drive using motor emulation. And finally, we'll present test automation applied to electric motor control. Now I'll hand over to my colleague Abhi Shankar, who will provide insights on how you can model electric motors and drives, both for desktop simulation and later for real-time testing.
Thank you. In this section, we'll look at model fidelity and setting up models for real-time simulation of motor and power electronics. Depending on your application, you can choose different levels of modeling fidelity for your motor and inverter. Based on customer feedback, our take is that for a basic E-drive proof of concept, you can start with the use of an average inverter and a lumped parameter motor model. For field weakening control, you can use an average inverter and a flux-based motor model. And if you're working on something like a torque ripple compensation, you will need a switching inverter and a spatial harmonics-based motor model. We can convert Simulink motor and power electronics models to HDL code. For piecewise linear components, we can convert Simscape electrical models to HDL-compatible state space models. By simulating power electronics on FPGA, you can reach simulation time steps below 1 microsecond and PWM resolution as low as 5 nanoseconds. This enables you to test your switching algorithm and compute the efficiency of your power electronics. Once your power electronics is implemented on the FPGA, you can start real-time simulation with just one click and observe the switching dynamics for switching frequencies up to hundreds of kilohertz on an oscilloscope or directly in Simulink using data streaming capabilities. Considering the inverter or any power electronics topology, as we discussed, we can choose different levels of modeling fidelity. An average model for the inverter is great for basic E-drive proof of concept. To validate switching events and analyze harmonics, we need a switched or subcycle average model of the inverter. As the switching frequencies in automotive reach from a few tens of kilohertz or hundreds of kilohertz for silicon carbide devices, simulating switching and harmonics requires a sample time of around 1 megahertz, which can be obtained by using FPGAs to run the plant model in real time. Taking a step back, power electronics is just turn on and turn off control. Timing matters a lot. An easy way to do power electronics simulation is just to take a lot of slices and run the simulation at every slice. That is a small time step. But for higher switching frequencies, like silicon carbide devices, we cannot take extremely small time steps. Let's say we can only take 4 time steps for 2 PWM cycles. Then if the current through the inductor should have looked like this, since we ended up capturing only part of the PWM transition, by simulating only the captured PWM in green leads to the simulated inductor current in red instead of the actual inductor current being represented in gray here. If you think of the harmonics in the inductor current, we just need 4 to 10 data points to represent that accurately, whereas PWM resolution needs hundreds of data points. If we could decouple these two, we could achieve a better simulation. Typically, sampling of switching frequencies happens at 50 to 100 times the switching frequency. PWM resolution is how accurately can you measure the width of the PWM. Simulation time step is how often are you updating the model states. Dotted lines here are the rate at which the PWM incoming signals are sampled. We want to decouple the model sample time from the PWM resolution. We could try an interrupt-driven method, but PWMs are not always symmetrical. An asynchronous interrupt method would not scale well. But building on these lines, we could decouple the model sample time and PWM resolution. The thick black lines here are the rate at which the model states are updated. That is the model sample time. To poll a TTL line on an FPGA is rather simple, so that can be done at about 5 to 10 nanoseconds, which is enough for a PWM resolution. Since most switches are connected to linear devices in simple topologies, using superposition, this method can be scaled up. Since the TTL is polled at the fast rate of 5 nanoseconds, we capture the PWMs accurately represented in blue. We can then use the ratio for how long the switch is on and off for each model sample time. Let's say it's on for 40% of the time and off for 60%. We average them together, just how average models are built. Here gray is the actual PWM and green is the effective subcycle average PWM through the simulated switch. In implementation, there's one model time step delay, so it's shifted by one model time step. We get the transition edges, we get the correct energy flowing through the converter. Because we get the correct energy flowing, we get the accurate ripple current as well. Motor fidelity can be categorized broadly into three levels. So we've got the lump parameter motor model, the saturation model that accounts for the torque saturation, saturation plus spatial harmonics model that accounts for the torque saturation and the ripple in the torque. We have motor models with different fidelities available in the MathWorks toolchain. For saturation model and spatial harmonics model, we need data from either dyno testing or FEA tools. We should be able to obtain flux data or the flux table. In order to feed the flux table to the saturation model, we must invert that into a current table. The lower two graphs here are the current ID and IQ tables. Here's the animation of flux variation at different rotor positions. The left plot comes from ANSYS Maxwell, which shows how flux density changes as the rotor position changes. And the right plot is a MATLAB plot of the flux surface at different rotor positions. You'll notice that the flux surface constantly shifts when the rotor rotates. That variation introduces spatial harmonic components in the flux linkages, currents, and torque. So in this type of high fidelity model, we're trying to capture the rotor position dependent component. We have examples of how to import reduced order models from FEA tools directly into MathWorks for desktop simulation from JMag, ANSYS Maxwell, and MotorCAD. The end FPGA compatible model would look similar to this snapshot. This is an FPGA compatible inverter and motor model. So this is a subcycle averaging inverter with gate inputs, DC bus voltages, and a fault word that sets it up for different fault scenarios that you might want to test for. And a motor model, again, which could be of different fidelities, being used either to drive it to a particular speed or with a particular torque load. And you can also have different types of sensors. Here we're using a quadrature encoder. Taking a look at the different time steps being used in this model, we can see that the gate signals come in at a much faster rate of about 5 nanoseconds. So that's the part we discussed, where we use subcycle averaging to get a better PWM resolution. And the rest of the system for the inverter and motor model states gets updated at 1 microsecond. So we put all of this in a harness model, which has been structured for how your interfaces would be on the hardware FPGA. later use the same model to generate HDL. We've also added a controller for desktop testing. So this model is open. You can press play and simulate it in desktop. That is one of the key benefits. So while you're creating an FPGA compatible model or using our FPGA compatible model, you can test it and compare it in desktop simulation before going to hardware. Taking a look at the simulation results, for a short sim time, this is what the current and speed in per unit looks like.
Thanks, Avi, for the insights. To wrap up, with this model-based design approach, we will use desktop simulation models also for real-time testing. We can use different levels of fidelity for our models and include high-frequency switching that is typical for wide bandgap devices. And finally, we can optimize desktop models based on experimental data. Now that Avi has shown us how to model electric motors and electric motor drives for different levels of fidelity, the remaining sections will cover 3 demos that reuse such Simulink-based models for hill testing of a controller, power hill testing of a motor drive, and also how to automate hill testing. Once we have validated the controller in desktop simulation, we can use the same plant models for hill testing. First, we deploy the Simulink-based controller to the embedded platform. In this case, we have an embedded microcontroller with motor control algorithms that uses a quadrature encoder and electrical measurements to control a motor inverter using PWM signals. And then also we deploy the motor and inverter plant model to the Speedgoat real-time target machine. The Speedgoat real-time target machine acts as a hill simulator that runs the motor and inverter models in real time. It captures PWM signals and generates quadrature encoded signals to emulate the motor rotation sensor, and it also generates analog signals to emulate the current and voltage measurements. Here is a picture of the hardware setup for our hill system. The Texas Instruments C2000 microcontroller is our system under test. It's also referred to as device under test whenever it's a controller. The hill test bench consists mainly of a hill simulator and I/O signal routing. In this case, the motor models and I/O interfaces are handled by a performance real-time target machine and an IO334 Simulink-programmable FPGA I/O module. Here is a block diagram of the hill system. When testing controllers, the system under test is typically referred to as device under test. In this case, the device under test is a Texas Instruments C2000 microcontroller with PWM generation, analog inputs, and encoder measurements. It also handles the speed and torque control algorithms. It interfaces with the FPGA I/O module running the inverter and electric motor models at 1 microsecond sample time. As it is connected to the microcontroller, its interfaces include 5 nanosecond resolution PWM capture, analog outputs for the current measurements, and a quadrature encoder emulator. The FPGA connects to the multi-core CPU via direct memory access or DMA. The CPU in the real-time target machine handles data logging, parameter tuning, and some plant dynamics. You typically use the multi-core CPU in the real-time target machine to run slower parts of the system, like it could be the mechanical transmission or the vehicle dynamics. We're going to use the HDL Workflow Advisor in HDL Coder for automatic HDL code generation and for FPGA deployment. We will also use it to define the I/O interfaces in the FPGA. Let's generate the FPGA application from the resulting Simulink model. For this, you can just right-click the subsystem in order to start HDL Workflow Advisor. Within the HDL Workflow Advisor, you can define the target as Simulink Real-Time, FPGA, and set the reference sign and define TTL lines, ADCs, DACs, and also PCI interfaces between the FPGA and the CPU. Then we also set the target frequency and we check the model for HDL code generation compatibility. Then we move to generating HDL code. The process to synthesize the HDL code takes some time, so here we're going to fast forward. Once code generation is ready, we can inspect the generated HDL code in the generation report and inspect traceability between the model and the code. Now we can call the Simulink real-time interface model. In this Simulink model, the FPGA subsystem on the right contains a call to the configuration file that was previously generated and that can be deployed to the IO334 FPGA I/O module. We're going to start the real-time model on the real-time target machine equipped with an IO334, and for that we are going to start the application using the Start Application button in Simulink. Now we're going to see the control interface for the microcontroller on the left and the signals from the Hill simulator on the right. We're going to use the control panel on the left to start the controller. The motor starts spinning in the other direction, and we can see the currents and the encoder counter. Now we're controlling the speed, and the virtual motor adjusts the speed as we adjust the reference speed. So it is like if the embedded controller was really connected to an electric motor. And now we can also see, for example, the phase A and phase B currents, which are, as expected, with a phase shift. We can use Simulation Data Inspector to explore the signals during execution and in more detail when we stop the real-time application. We go back to the Simulink model of the motor and the inverter. Here we can change some plant parameters while the real-time simulation is running. For example, let's increase the torque load from 25% to 95% of the nominal torque and inspect the results. As expected, after a dip in speed, the controller regulates the speed and the currents increase. We now stop the real-time application and explore the results in Simulation Data Inspector. We have one phase current on top and the speed below. We can easily visualize more signals. Here, for example, we add another phase current plot. In some cases, your microcontroller also needs to communicate to other control layers via protocols. Speedgoat provides a wide range of communication protocols ready to use. To wrap up, we've used HDL code generation to deploy a motor and inverter plant to an FPGA that runs at 1 MHz and used for hardware-in-the-loop testing. We also implemented FPGA interfaces such as PWM capture, and we leverage industry protocols. We'll now present a motor emulation demo that is used to test electric motor drives. Now that we have thoroughly tested the embedded motor controller using hardware-in-the-loop testing, we can integrate the embedded controller with the real motor inverter. But how to test the motor inverter safely before connecting to the rest of the electric motor and the rest of the electric vehicle? It could be the case that the electric motor is not yet available. We can then use Power Hardware-in-the-Loop, or Power Hill for short, to emulate the motor and also the battery pack. Motor emulation is a test procedure where you can emulate the electrical behavior of an electrical machine, and it is typically used to test motor inverters. You may want to test the inverter against a motor connected to other systems like hydraulic pumps, conveyor belts, or transmission systems. For example, you may want to test the inverter of an electric powertrain for different driving conditions. You can also consider both electrical and signal faults, or even test different types of motors without disconnecting your motor emulator. If we isolate our motor inverter as a system under test, we would be effectively cutting the electrical links, sensor and control links. We can close the link between the system under test and the rest of the system by using a Hill test bench composed of at least a power amplifier and a real-time target computer. You will also need a simulation of the rest of the system with I/O connectivity to emulate encoders, sensors, and other signals that the system under test may be expecting. Let's see a brief demonstration. In this case, we'll emulate an induction machine connected to a load. There is also a resolver being emulated and connected to the motor inverter. As equipment under test, we will use an off-the-shelf motor drive, a Siemens CMOVER drive. The power amplifier is a 4-quadrant Compiso system unit from Exton Power. And finally, we'll also connect an oscilloscope with voltage and current probes to the electrical connection between the motor drive and the power amplifier. Let's start the testing. We go to the interface for the Compiso system unit from Exton Power first, just to make sure that the reference is set to come from the Hill simulator. And then we enable the power amplifier. Then we go to the Simulink model. The model can be deployed in the FPGA or in the CPU, and in this case we'll be deploying it to the CPU. The model includes an induction machine that could come from Simulink on Simscape Electrical and could also include nonlinearities or FEA data. We have an external torque that may be set manually or come from the plant simulation. And we have an interface to the power amplifier using the Aurora protocol and also an interface to the resolver emulator. Both the Aurora protocol and the motor emulator run in the FPGA. As we start testing, we will be showing from left to right the Siemens drive monitoring and control panels, the oscilloscope screen, the Compiso interface, and the Simulink interface to the virtual motor. Let's start by setting the frequency of the drive to 50 Hz. It corresponds to the motor rated speed of 1440 RPM. We can see that the resolver signals are being displayed in the inverter panel, and we see that the voltage and currents are displayed in the oscilloscope. Initially there is no torque load being applied and the currents have a phase lag. We are going to increase the external torque manually. As we increase the external torque load in steps, we will see the current amplitude increase. This shows how the motor drive and the virtual electric motor that is running in real time are synchronized and respond instantaneously to the changes of each other. Motor emulation has many applications and can be used for test automation at full electric power, test typical operation and fault conditions, and also emulate different types of electrical machines, include saturations or spatial harmonics, and involve also different types of loads such as electric vehicle transmission, pumps, conveyor belts, etc. And you can also include with the real-time systems, resolvers, encoders, and other sensors you may need. We have now seen two different types of Hill testing for motor controls. One being Control Hill, that is focused on testing embedded controllers, and also Power Hill, where we emulate an electrical motor and test a motor inverter involving real electric power transfer. Now let us see a demonstration on how to automate Hill testing. Specifically, in this section, we'll discuss how you could implement different test scenarios, automate testing and perform validation, compare Hill results against desktop simulation, generate test reports in different formats, and even leverage continuous integration with Linux. For automated hardware-in-the-loop testing, we're going to use a test harness. A test harness being an encapsulating Simulink model that allows us to connect multiple test inputs and verification statements to our system under test. A test harness can quickly be created for any model by right-clicking and selecting Test Harness, Create for Model then. In this case, we already have a test harness in place. We can quickly go to it by using the Perspectives view on the lower right. You can see that this looks like any other Simulink model, but it includes a reference subsystem with our system under test, and we are using the test sequence block to define the input signals for the different test cases. The test sequence implements closed-loop testing using step transitions. At 1 second, the motor is turned on, followed by a verification step where we check that the measured velocity lies within tolerance. We repeat this process with a velocity command in the opposite direction and verify again. We can run the test sequence in desktop simulation first, add breakpoints to the sequence for debugging, and then manually deploy the model for real-time execution. Notice that you can quickly end up with multiple models and test harnesses. We can avoid managing them all manually by using the Simulink Test Manager for full test automation of our test management, execution, and evaluation for both desktop simulation and real-time testing with hardware in the loop. We can open the Test Manager directly from the Simulink toolstrip and see our pre-built test setup. The first test is named MIL, or Model in the Loop, so this will run entirely in desktop simulation. The second one, for rapid controller prototyping, is then a real-time test, which means that the model will be executed on a real-time target machine. You do not need to create each test from scratch here. We can easily make a copy of our desktop simulation test and convert it to a real-time test. Like this, you can maintain the configuration, such as assessments and parameter overrides. Now I'll be using the test for hardware in the loop, which is a real-time test set to be executed in a hill simulator. Here we define the model to run and the test hardness to apply. We're also overriding some model parameters. In this case, we are changing the inertia of a disk that is attached to the rotor to evaluate the controller's response. Finally, we have multiple assessments which will be automatically evaluated to determine if our test was successful. These come in addition to the verify statements in our test sequence block. So let us run the test case by clicking the Run button. The test runs for each parameter set automatically. As it takes a bit of time, we will fast forward to the results. At the end, we can immediately see from the results that the test passed. For more detailed analysis, we could see plots of the signals, and the outcome of the verifications can also be visualized. Once we have a complete set of results, we may want to export them for a later analysis or documentation. We can select the test cases we want to generate a report for and click the Report button. There are multiple fields that we can customize and check boxes to enable which content we want to publish. In this case, we are going to create a PDF report including plots of the assessments and simulation outputs. After just a few seconds, we get the complete report for later analysis. So, while this was a real-time test case, your test suite can also include desktop simulation test or equivalence test, where you verify that different models produce equivalent results. Let us use this to compare our desktop simulation model to the hill variant that is connected to the embedded controller. Again, both models are built and executed automatically, and we'll be fast forwarding to the results now. As you can see, the rotor velocity in both runs lies within the specified 15% tolerance, actually never even exceeding a 5% difference. We could again generate a report in Word, PDF, or HTML format. And from our test browser window, we can then run the entire test suite in one go by selecting the respective section before clicking Run. This can save you a lot of time because the lengthy process of setting the parameters, compiling and running the models, and even evaluating the data, it is fully automated. You don't even need to open Simulink anymore, as configuration, execution, and evaluation is all handled by the test manager. Another step in test automation is continuous integration, or CI for short, where you automate the building and testing of software. A lot of times, a CI workflow starts in your machine, as you're using MATLAB and Simulink to develop controller software, test cases, or plant models. As soon as you commit or push your changes to source control, that will kick off a continuous integration job on a CI server that runs a batch of tests that qualify your contribution to the project. And it also creates test reports automatically to tell you what failed and all the information that you need to fix eventual issues. You'll fix the issue, recommit the changes, and that cycle will continue. So this makes controller software development and testing iterations a lot faster, and it allows you to kill bugs right when they were created. So we see CI can help with many of the challenges previously mentioned with clear benefits. Repeatability is a huge one. CI allows you to centralize the testing and provides you with a consistent and repeatable environment. Quality, as you're continuously testing the latest changes. You're also improving the speed at which you develop by testing early and testing often, and nothing is left behind. Collaboration is another one. The earlier you identify integration issues, the less expensive they are to fix. And finally, you're creating a trace-ready system so that when you do find an issue, you know where it comes from, who introduced it, and how long it was present on the design. All gets documented and tracked, something that is critically important as your organization scales or as your application becomes mission-ready or safety-critical. The good news is that MATLAB and Simulink can help with many of the CI tasks in hand. For instance, you can use source control within your projects, quickly track and compare and qualify changes, and quickly visualize and report results of your automated testing. You also benefit from off-the-shelf integration with the main CI platforms like Jenkins or GitLab, allowing you to quickly implement cloud and on-premise CI servers. And the best of it, all can be orchestrated to work with hardware and complement your Hill testing workflows. We are at the end of this webinar, but before leaving, we would like for you to take 3 ideas for this session. First, that you can use Simulink and Simscape Electrical to carry out real-time simulation of electric motors and drives in both CPU and FPGAs. Second, that you can use real-time simulation to test controllers and electrical equipment against virtual plant models. And third, that you can perform test automation for Hill testing using Simulink Test and other third-party products. Thank you.
You want to learn more about real-time controls testing? Then find additional content linked here.